We played around with sequences, wrote some terms, found some rules. Now we've also found some limits. Now we're going to introduce some of the basic vocabulary that we need. And the main two words that we need are convergent and divergent. So we're going to first go ahead and define what those two words are, because we're going to be asked if these sequences converge or diverge. So, simply put, if a sequence converges, that means that the limit exists. That's all it is. The limit exists. That's all converges means. To say that a sequence is convergent means that a limit exists. Well, then what about divergent? Divergent means the limit of that sequence does not exist. Stop. Convergent means the limit exists. Divergent means the limit does not exist. And that's it. That's all there is to it. Now, before we actually get to these, I want to make sure that we understand the hierarchy of functions that we had from Calculus 1. Okay, this is very good to have, especially if you're in computer science and you're probably going to be taking analysis of algorithms soon. You're going to analyze some of these sorting and searching algorithms. So we have four basic functions here. Log of n, 1, the constant function, power functions, that's a funny looking n to the p, okay, b to the n, and because I can't count, we have 5 basic functions. Because the last one at the top of the hierarchy here is the factorial, okay? So let's go ahead and get these names, okay? So we have factorial, exponential, power functions, constant functions, and logarithmic functions. All right. If it's at the bottom of the list, that means it's slow, and if it's at the top of the list, it's fast. So we're going to go here. This is the slowest growth. And going up, we have the fastest growth. All right. So bottom is slowest, the top is the fastest. All right. Now, how does this help us? If you remember from Calculus 1, when you looked at limits at infinity, you want to see, which term dominates in the end, blah, blah, blah. This is the kind of thing that you were thinking about. Okay, this is the sort of thing that you were thinking about. So let's take a look here. We have a sequence, 1 over 5 to the n. Does the sequence converge or not? So we're asking, does this limit exist? Okay, so we are looking to compute the limit as n goes to infinity of 1 over 5 to the n. Well, I have a constant function being divided by an exponential function. The exponential function grows much faster than a constant function. So if I divide a constant by an increasingly large number, what's going to happen? Well, I'm just going to get an increasingly smaller number. So this limit here is 0, okay? Because the denominator, it dominates the whole thing. The exponential grows much faster than the constant function. Okay, just some reasoning there, okay? How about this next one here? N squared over n plus 1. That's like a limit that we saw in Calculus 1, right? Okay, and we did something like this before. Oh, and by the way, I should say, okay, before I forget, because the idea is not just to find the limit, we need to classify convergent or divergent. This sequence here, this sequence is convergent. Okay, because the limit exists. Okay, the limit is 0. Okay, so again, if the limit exists, that means we have a convergent sequence. All right, so let's take a look at this next one here. N squared over n plus 1. Okay, we have two power functions, quadratic over linear. What is the highest power that appears? It's a square. So we're going to divide top and bottom by n squared. So let's write this here. N squared over n plus 1. I'm going to divide top and bottom by n squared. So we have n squared over n squared, n plus 1 over n squared. Now we need some cleanup, right? On top, I just get a 1, a constant, and on the bottom, we have, well, if I divide everything correctly, 1 over n plus 1 over n squared. Uh-oh. Looks like we got a problem here. 1 over n goes to 0. 1 over n squared goes to 0. We know this, right? But 1 divided by 0, well, that's not good, right? Okay, think back to when you actually did this, right? You can also think about this with the long division. If you did long division, as we saw in the partial fractions videos, okay, you get a polynomial plus some garbage. Well, the garbage will go to 0. Polynomials will just explode. Okay, think about this. I'm going to have 1 divided by, well, 1 over small number is a very, very, very big number. Divide a constant by something tiny, you get a big number. Okay, the limit does not exist in that sense, okay, because we have a 1 over 0 here. So let me put this in red here. We have a 1 over 0. Okay? The limit does not exist here. Okay. So the sequence is divergent. Okay? The limit does not exist, or I should also have said the limit is infinity or minus infinity. Then we say that the sequence is divergent. Okay? The limit does not exist in this case, so we have a divergent sequence. Okay? If you are very say a bit removed from your limits from calculus 1, I highly encourage you to go back and review those basics. Okay. Log of n squared over n. Okay, this one's interesting. Well, if I look at this as a limit here, well, log of n grows kind of slow. Okay, n squared kind of goes a bit faster, but does that mean that I get 0? Well, if you think about the hierarchy of functions, okay, power functions grow faster than log functions. So the denominator wins and the limit is 0. But how can we rigorously show this, okay? This is another thing that we should have recalled from calculus 1, okay? So now let's take a look here. In fact, to simplify this a little bit, I'm going to do the following. We have log of n squared over n, and what I can do is use a log property. If I have log of something to an exponent, the exponent comes out as a scale multiplier. So what I'm going to do is log of n squared is the same as 2 log of n over n. And we probably saw integrals like this in the improper integral section, okay? But now, if you think about this, intuitively, if we plug in, so to say, we get infinity over infinity. But what do we do, right? Log of n over n? Get infinity over infinity. Surgical procedure? Use L'Hopital, okay? We need to use the L'Hopital rule here, okay? You need to use L'Hopital, okay? So we're going to take derivatives of numerator and denominator separately. So we have this limit here. Derivative of log n with respect to n is 1 over n, so the numerator becomes 2 over n. My denominator is just 1. And now this is easy. I get a 0 over 1, which is fine. We get a 0. So the limit is 0, and the sequence converges. Sequence converges. Okay. Now, again, fair warning, remember, L'Hopital, you only use that if you get a 0 over 0 or infinity over infinity or any other indeterminate form. Don't do it just because you're dividing by 0, okay, or just because you have a fraction, okay? Don't do that, okay? Only if you have infinity over infinity, 0 over 0, or any one of those other fancy indeterminate forms like 0 to the 0, infinity to the 0, or anything like that. All right, so we have a convergent sequence with limit 0, okay? Let's look at this one. N over 3, n times 3 to the minus n. I almost gave it away a little, okay? N times 3 to the minus n. Well, let's think about how to rewrite this, maybe. So I want to find this limit. Okay. N over, well, I just gave it away. So we have n times 3 to the minus n. Remember exponent rules. Okay. N over 3 to the n. All right, now let's think. I have infinity over infinity. So I should use L'Hopital, okay? Now, if you're clever enough, you should be able to see that like this limit is going to be 0, but we'll show it with L'Hopital, okay? So let's make that note here. We have infinity over infinity, L'Hopital. Okay, we're going to use the rule of L'Hopital here, okay? So the derivative of the numerator is easy, okay? You just get a 1, but what about the denominator? That's 3 to the n. Okay, just a fact here, okay, if you remember, the derivative with respect to x of any other exponential function, base b, b to the x times the natural log of b. Here our base is 3, so we're going to do the same sort of thing. So the derivative of the bottom here is 3 to the n times natural log of 3. We'll have a constant, 1, divided by, well, I can ignore the log 3 there, okay, divided by an exponential. That's going to shoot down to 0. So this whole limit is 0. And so this limit is 0. The sequence is convergence. Okay, remember. Okay, we need the limit to exist and be a number, okay, a finite number, in order to say that the sequence is convergent. It doesn't have to be 0. It could be something like 2 or -1 or, pi squared over 6. So long as the limit exists, okay, then we can say it's convergent. So here's another one we're going to use some log properties. Log of 2n plus 1 minus log of n. All right, let's take a look at this limit here. So we have the limit as n goes to infinity of, let's just write down what we have here, log of 2n plus 1 minus log of n. And remember what logs do with differences, right? The difference of logs is the log of a quotient. Okay? So we'll have this, and we have the log of 2n plus 1 over n. Stuff over common denominator, I can separate. So when I do the separation here, we get the limit as n goes to infinity of the log of 2n over n is just 2, and then plus 1 over n. Now, I'm going to go ahead and use a bit of a fact here. I know that log is continuous on its domain, and I'm allowed to pass limits through continuous functions, okay? That's a result that I can do. Okay, I can pass limits through continuous functions. So I'll write this as the log of the limit as n goes to infinity of 2 plus 1 over n. Well, 1 over n goes to 0. The only thing left over there is 2, so I just get a log 2, and so the sequence converges. The sequence is convergent. All right, let's go ahead and do this last one here, okay? Sine squared n over 2 to the n. Okay, this looks a little funky. There's a couple of ways you can do this. Okay, and in fact, I'm going to go ahead and relate this back to a limit that we may have seen before, okay, in Calculus 1. Okay. In fact, actually, yeah, let's go ahead and do this here. So we're going to have the following. Okay, so let's state this as a fact here. Sine of x over x, okay, we take the limit here, the limit as x goes to infinity of sine x over x is 0, okay? Might need to make a cut here. And in fact, I will. You may have noticed there was a bit of a cut in the recording, and this actually is right. Now, justifying it, we got to use a little something called the squeeze theorem, okay? We're going to have to use the squeeze theorem. Remember that result? Use the squeeze theorem here, okay? So if I have 3 functions, f, g, and h, and let's say this, f of x goes to L, h of x goes to L, okay? As say x goes to c, then the thing in the middle, it's trapped. It's got nowhere to go. Okay, I just realized it's behind my head. All right, let's go ahead and fix that. So if we have this, then g of x, the thing in the middle, goes to L. It is squeezed. So how are we going to work with this? Okay, so let's do a bit of thinking here. Okay, we're going to use another fact, another fundamental inequality here. Okay, remember that sine of x is between -1 and 1, and in fact, well, right here, sine squared of x is between 0 and 1. All right, so we're going to do a bit of very clever thinking here. All right, so here's what we're going to do. We're going to look at sine squared of n over 2 to the n. Now, I know at least because sine squared is positive at the very least, okay? And certainly the denominator is always positive, right? 2 to any positive number is positive. I know that that thing is going to be greater than or equal to 0, possibly, okay? On the right, however, I can replace sine squared of n by 1. I know that the largest that the sine squared of n can be is just 1. We'll replace this by 1 over 2 to the n. All right? So, this 0 here is like our f of x, or f of n. This is like our h of n here. And this is our g of n. All right, so now you might be able to see where this is going, okay? Now, take a look here. The limit here, as n goes to infinity, of 1 over 2 to the n is 0. Okay, 0 is constant. I have 1 over 2 to the n that's going to 0, and this other thing in the middle, sine squared n over 2 to the n, is trapped in between 0 and 1 over 2 to the n. So it's got no choice but to be squashed down to 0. So by squeezing, the limit here, as n goes to infinity, of sine squared n over 2 to the n is equal to 0, and the sequence converges. The sequence is convergent. So this one was a little tougher. But what was the idea for a lot of these, right? Do we have a limit or do we not have a limit? That's it. That is all you need for convergence and divergence. The only question you should be asking yourself is, does the limit exist? Okay, and is it a finite number? And that's it. That's all you need. Okay, we're going to go ahead and finish this off and talk about one more property of sequences, two actually, boundedness and monotonicity. I'll see you in the next one.